All right. Hi, everybody. My name is Shannon Woods. I work for NVIDIA. I'm also the chair of the newly formed Slang working group at Khronos. And I'm here to talk to you today, not just about Slang, but what it does for neural graphics. So there have been a handful of presentations in other venues, both from me and other folks involved with Slang, that introduce the language itself and talk about some of the core language features like generics and interfaces that bring something new to the shading language space. And I'm not going to go into deep detail on a lot of those features today, but if you catch up with me in the hallway, I can point you at a bunch of materials that do dive into those things. But if you're not already familiar with Slang from those earlier presentations, I can give a really quick overview for you. Slang is both a shading language and a compiler that ingests that shading language and outputs to a number of different formats for use across different APIs and platforms. Slang's syntax is similar to HLSL, but with some additional modern language features, which help with managing the scope and complexity of computer graphics code. Slang also provides helpful on-ramps into Slang from HLSL and GLSL. It's able to compile most HLSL and GLSL syntax as is. There was a question in the last presentation about why you wouldn't want to just use Slang. It's because that's most, and HLSL might decide to adopt new features in the future that we can't guarantee will come to Slang. So since this past November, Slang has become part of Khronos. That allows multi-company governance while still doing all of our technical development fully open source. Our developer community is thriving. We've got over 3,500 GitHub stars, which actually surpasses our peer shading language compilers. And our Discord, which you can join with this lovely QR code, has more than 430 members. On Discord, you can find developers engaging daily on our support channel. You can ask questions and get them answered both by the core Slang team and members of our community. And you can participate in discussions, make language proposals, or discuss the implementation details of something that you're working on in the compiler in our dev channel. We've also got a cool showcase channel where people are sharing things they've built in Slang or useful helper libraries that you might want to use if you're getting started in Slang. So there's a lot of stuff to check out there. Please give it a join. Now, we've been getting a lot of great feedback and contributions from the community, and that's driving lots of improvements, fixes, additions in the last 2 months. Specialization constants and push constant improvements. I believe a lot of this has been contributed by community members, which is really cool. We've also got improvements to the reflection API and how you do binding. We added a lot of documentation for that. I personally am on a big push to get us more and better documentation. So please keep filing bugs about anywhere where something is not clear. And then we also just recently added bindless support. We've gotten a lot of requests for that. So Slang now provides a descriptor handle T generic. It can be used like a simple pointer to T. And then when compiling to SpearV, Slang will use descriptor aliasing under the hood. This is how you do the same thing yourself, except now the compiler can handle the messy details for you. You don't have to worry about it. It's also portable across other targets that provide a mechanism for bindless support like D3D. So lots of stuff going on with the Slang community today, but the part I'm going to focus on in this presentation is neural graphics, because there's transformative stuff going on right now. So other folks have touched on this and will touch on this in their presentations, but one of the things driving Slang forward is that neural techniques are making their way into graphics. And what I mean by that is that developers are taking machine learning approaches to solve traditional graphics programming problems. And that's in addition to the advances made on cool novel areas like scene synthesis and reconstruction using stuff like NeRFs and 3D Gaussians. This is really the next frontier for rendering. So the thing that makes Slang the right tool for neural techniques on the GPU is automatic differentiation. If you're not familiar with the how and why, I'll zoom in on that for a minute. Differentiable functions are at the heart of gradient descent approaches to optimization, which show up across the graphics world. For example, 3D scene reconstruction and differentiable path tracing. Now, traditionally, performance-critical, real-time, differentiable code had to be written by hand. So you had to write and maintain 2 copies of your shaders, both the original and its differential. And any changes that you make to your original shader, you have to make the correct corresponding changes to the differential form. That is a headache. And people have been willing to do that in research, but if you're looking at a production code base, that's a problem. So support for automatic differentiation is built into Slang. What this means is that you only have to annotate your function as differentiable, and Slang will automatically generate both the forward and backward differential forms. So this has a huge impact on maintainability. What's shown here on the screen is the backwards differential form of just part of the algorithm for the rasterizer from last year's paper. It might be the year before last at this point, 3D Gaussian splatting for real-time radiance field rendering. This part is just the diff of the function where it derives a covariance matrix from the Gaussian's rotation and scaling matrices. There's more to the algorithm than that, but looking at this, the point I want to make is that this is a pain to read. It's even more of a pain to write. And if you make any changes to the original forward form, you have to make the correct changes to this differential form. And getting that right makes it really difficult to iterate on your design. By contrast, this is much simpler in Slang. It can be written in its forward form and just annotated as differentiable, and the compiler takes care of the rest. It's easier to read, easier to maintain, and easier to debug. So looking at a comparison between the original handwritten differential rasterizer and the Slang version, which was authored by George Kopanis, one of the original paper authors, he was able to get a 40% reduction in lines of code while maintaining equal runtime performance to the handwritten CUDA. But it's not just novel areas of research that can make use of Slang for neural techniques. Neural techniques can also provide performance and quality wins for traditional graphics problems. For example, researchers are finding new ways to compress textures. Now, the process of texture compression is that for every 4x4 block in the image, you find a pair of endpoints in color space and map each pixel to a value along the linear space between them. And then you can encode the entire block as a pair of endpoints and 16 quantized one-dimensional locations. This can be framed as an optimization problem. There are lots of sophisticated algorithms for doing texture compression that represent trade-offs in speed and quality. But with Autodiff, you don't actually need to understand any of that to write a texture compressor. We can do it by learning. And this is a really simple 3-step approach. So first, we write a decompressor according to the spec. Decompressors, very straightforward. Next, write a loss function that compares the decompressed image with ground truth, the original image. And finally, just differentiate that loss function and plug it into an optimization loop. As you can see, you don't need any knowledge on image processing to write a compressor. In this case, compressing the image is a difficult problem, but the inverse, a decompressor, is trivial. So stochastic gradient descent allows us to solve a hard problem by simply implementing its trivial inverse. So great! Automatic differentiation in Slang enables neural techniques to be written and easily maintained in shader code. So we can take advantage of everything that machine learning has to offer when we're writing our graphics code, right? Not quite. There are 2 separate ecosystems that ML and graphics developers have built around their use cases. So if you work in machine learning or computer vision today, you're probably working in Python. and use packages like PyTorch, JAX, or TensorFlow. But if you work in graphics, you write the code that executes on the GPU in a shading language, and you write C++ to call the graphics APIs in Vulkan and launch your GPU code. This fundamental difference in programming models and languages and the isolation of the ecosystems make it very difficult to reuse work across that boundary. Now, you could consider moving all of your ML work into the graphics ecosystem, but the tools and languages on the graphics side are a poor fit for the rapid prototyping and iteration that ML research and development needs to do. No one wants to deal with that much C++ boilerplate, even us. And re-implementing the infrastructure, all of those frameworks and collaboration tools that exist in the ML world would take years. And graphics in the ML world is also a non-starter because graphics can run drastically different sequences of operations depending on runtime conditions like what surface array hits. So it needs dynamic control flow on a per-thread basis. So our approach is to build a bridge between the worlds. We have Slang, which provides automatic differentiation as a first-class citizen, and allowing for implementation of neural techniques in a shading language. And then to make Slang transparent, easy to use, and iterable from Python, we've added SlangPy, a simple pip installable package which provides mechanisms for using Slang within Python regardless of your ML framework of choice, without needing to generate lots of integration boilerplate. So taking a look at what it looks like, without SlangPy, you still have everything that Slang has to offer for writing kernel code, but even with the help of a rich featureful library, the setup and dispatch from C++ is irritatingly verbose. This isn't new for anyone in this room, but it's a big problem for people who are used to the flexibility and rapid iteration of ML Python frameworks. So SlangPy makes using Slang directly from Python simple. All you have to do is load the Slang module from your Python code and then call one of the functions inside. You can pass a PyTorch tensor or a NumPy array or a basic Python array or a dictionary, and SlangPy will take care of marshalling it. Now, if you haven't started using neural graphics techniques yet, you might ask, what kind of problems can I solve with this? What does training even mean? So I'm going to take a simplified version of the 3D Gaussian rasterization problem that I was showing just a moment ago. And for simplicity's sake, we'll think about what we can do in just 2 dimensions. Now, Gaussians are just a basic way of representing a scene or an image. And our 2D Gaussians here are going to have just a couple of parameters. There will be a 2D float representing the center of each splat, a float representing the sigma value, which is the standard deviation of the Gaussian distribution. You can think of that just as the coefficient of splattiness. So a big sigma value means it's large and diffuse, and a small sigma value means it's tight, focused, and concentrated. And the last parameter is just color. So you can represent a 2D image as a bunch of splats. And you could randomly generate a bunch of splats to get basically a 2D image of noise. That's what this very colorful thing in the middle is. But how do you know what values the splats need to have in order for them to be something meaningful, like an image of a Jeep? That's where the training comes in. So to compute the value of a particular pixel from a set of Gaussian splats, it's really simple. You just go through your collection of Gaussians and determine the color of each splat at that point in space and accumulate. This function does just that. But you need to know not just what are the pixel values for a given set of Gaussians, but what should the parameters of all of the Gaussians be in order for these pixels to be a picture of a Jeep. So you need to train your model. Basically, you have to have a way of expressing how different of this pixel is this pixel from what I wanted it to be, so that you can optimize that function for as not different as possible. And that way of expressing the difference between the current value and the target or ideal value is the loss function. So for a 2D image, defining the loss function is also really simple. You just have to calculate the difference between the inferred pixel, which is the one that you get by accumulating all your Gaussians, and the one that you wanted to get, which was the pixel in the reference image at that location. Then we take the dot product of that vector with itself to find the square of the magnitude. So in very simple terms, it's a big number if they're very different and a small number if they're really close to the same. Great, so how do we optimize for the smallest possible loss? We know optimization problems are generally just a little bit of derivative calculus, and that's what drives the technique of gradient descent. So if we can calculate the loss, then determining what parameters give the minimum possible loss is a matter of calculating the gradient. In our case, it's the derivative of that loss function with respect to each of the parameters of all of the Gaussians. Now, if we were talking about just a couple of parameters, you might be able to visualize that optimization problem as looking for the lowest point on a 3D graph like this one. But typically, with the sorts of problems that are interesting to use gradient descent for, you'll be dealing with a very large number of inputs. Though in the case of our 2D splatter, it's just a couple 100,000 at most. So we need to take the partial derivative of our loss function, which includes looping over all of our Gaussians to accumulate the color, with respect to each of the input parameters, that is, each of the positions, sigmas, and colors of all of our Gaussians. Slang makes that calculation really easy by automatically computing the backward derivative for you. You can see here from Python, we're invoking the backward differential form of the per pixel loss function that we created in Slang just by calling the BWDS function. I guess I can pronounce it backwards. We pass the output parameters so we can accumulate the results of the loss function, the UV position of the pixel, the set of blobs with their current parameters, and the target image. So worth noting, you might have noticed across the last couple of slides in the code, we've specified a couple parameters as tensors. Both the output of the loss function and the set of blobs are tensors. And the reason is because we have to associate gradients with them. So after we've invoked the backward differential, we end up with per pixel loss here storing the results of the loss function, which we have so that we can detect when we've hit the threshold where we're happy and we're going to stop iterating. And then our blobs each have an output gradient, which is the derivative of loss with respect to each of the blob parameters. That tells us what direction we need to move the parameters of the blob in order to get closer to our target and make the loss get smaller. We then go through and update all of the blob parameters based on this information and end early if we've dropped below the loss threshold. SlangPy also provides convenient ways to deal with all of that tensor data. So SlangPy tensors are interoperable with NumPy arrays and PyTorch tensors, which is really powerful because that gives you an easy way to get data that you may have worked with in other ML contexts into Slang. Now, the full implementation of the differentiable 2D splatter has more to it. There's alpha blending, some logic for sorting blobs and determining which ones intersect parts of the screen, so you're not doing a bunch of calculation on blobs that don't matter. But in total, the entire thing takes only 90 lines of Python and then 800 lines of Slang, and that's just the human-written forward code. You can also check it out and see it running in action, rendering each iteration as it goes in the browser on our web GPU-based playground at the link right there. And you can come see me. I've got it running on a laptop out in the hallway. If you want to see the WebGPU version. Notably, WebGPU does not involve Python. The Python version you can find in our examples library, which I'll give you a link for right here. So the things I want you to take away are that Slang opens the door for neural graphics techniques. Slang and SlangPy work together as a bridge, making it easy to bring neural rendering into machine learning contexts and vice versa. Basically, it's a way to work with data that you may have already been using in the other context. And the neural techniques benefit not just stuff like scene reconstruction, NeRFs, and Gaussian splats, but they also bring new ways to address traditional problems like texture compression or fluid simulation, or basically anything where you need to optimize across a ton of parameters. So you can get started with SlangPy. We've put up a collection of samples in our repository. So start tinkering around. And if you have any questions, people are waiting on Discord to answer them. So, but if you have any questions right here, I am waiting to answer them. So
I have a question about the Autodiff. So with the forward differentiation, if you've got like really long functions, then the chain rule explodes the code size. And if I remember correctly, like in HPC High Performance Graphics Conference in 2022, when Mitsuba 2 was announced, they said that essentially when you've got a path tracer, like the amount of forward differentiation code was so large that they've run out of memory for the generated source. And they had to do the backpropagation, reverse differentiation, but they also had to make it stochastic to actually make it tractable. And the question is, does Slang have any of that for the backwards differentiation?
that is a question I would have to refer to Saibangru, who architected a lot of the automatic diff in Slang. I can't say off the top of my head. I haven't run into that question before, but I'm going to find out myself because now I'm interested. He's on Discord. You can ask him.
Cool. Quick question and then a comment. The quick question is just for a simpleton like me that lives in traditional rasterized triangle rendering land, other than these fantastic examples, what would you recommend as a way to get into neural graphics in a real-time way?
So the 2D Gaussian splatting example is the way that I got into it. I'm actually also relatively new to the ML graphics space. I think that honestly, working with something small where you can keep it in your head is a good way to kind of get your head around it before diving off the deep end into having to optimize across literal millions of parameters.
And then just the comment is, I just want to repeat my slavish praise that I heaped upon you when I met you yesterday. Just for context, our team ported about a couple thousand lines of GLSL to Slang in November last year in about a week. We used some, pretty modern features like buffer device address that unfortunately weren't working in HLSL. So that turned to be a non-starter for us, and the process of moving to Slang was just brilliant and fantastic. I think we opened 2 issues, and they were all solved within 24 hours. Your team is freakishly good at doing that. So I just want to say you guys are amazing, and if anyone is considering Slang, do it.
Thank you.
Hi, Shannon. Yeah, just one comment here, basically for the benefit of everyone, is that you used the example of compression into BC7 mode 6 for illustration of how to do neural graphics. And I should just warn everyone that that's not a good way to do BC7 compression. It really gets you a very, very slow compressor, and only for one mode, which is very low quality.
I will refer to several talks yesterday with the I have committed small lies. That is one of them. It's a toy example, but the main thrust of the argument, basically, you can solve some complicated problems by doing the trivial inverse holds. It's just sometimes there are other influencing factors.
Yes, it's a good example, just not a very practical one in that specific case.
Yeah.
I have a question. So how much heavy lifting does SlangPy actually do? Because what you've done is you've shown a bunch of Vulkan developers you can load a shader and then execute it in one line. So can we now write a renderer in Python that's performant?
So the renderer part is not implemented by SlangPy. There's a helper library in the middle, SGL, that's handling a lot of the rendering stuff for you. I also don't know how much of the render to screen happens through the SlangPy stack. So asterisk there. I don't think you're going to want to rewrite your entire complicated renderer in Python.
But
It's mainly convenience so that you can take huge ML data sets that you've been working with and start doing cool rendering stuff with them.
Okay, thank you.
Thank you for the presentation. So I had two quick questions. If I wanted to do the Gaussian example fully in C++, how easy is that?
Not terribly hard, actually. So I can link you to the presentation that I did at SIGGRAPH Asia. Links out to the full 3D version in C++ and Slang.
Right.
So yeah, not awful.
Cool, thanks. And then Slang looks awesome. Assuming I'm going to like do all my Vulkan stuff in that, are there any kind of holes or bits of missing functionality I should be aware of in terms of like going for extensions, or is it all pretty much there?
So core, I think everything in core is all there. Extensions, I don't know about the status of various vendor extensions. I haven't gotten reports of any like widely used things that are missing. But if there's stuff you want that's not in there, please file a bug. We will add it.
Thank you very much.
One of the things that both GLSL and HSL have added recently is SPIR-V intrinsics, so the ability to directly insert SPIR-V code for extensions that aren't exposed in the language yet. Is that something that Slang has as well?
Yes.
Well, that was easy.
Okay, so any other questions? Okay, for another, thanks to the speaker.